Okay. Good afternoon, everyone. Now we are going to start the unit number 4 today. That is the gaseous state of matter. Right. Now we know that the matter is anything that occupies the mass and space. Right. That means matter is anything that has a mass and which occupies free space. Is called a matter. That is the definition of a matter. And that matter can be divided into three categories. They are solids, liquids, and gases. And if we consider this matter, it is divisible into three. As solids, liquids, and gases. Right. So these are the three main states of matter. Right. Of them, we know what solids are, we know what liquids are, and we know what gases are. And now let's consider the properties of them, and let's see how these properties will change in with respect to the intermolecular forces in between these substances. Right? Those properties will be changed due to the various intermolecular forces. For example, in solids, the particles are tightly packed. Right? So the particles they are tightly packed, so that the particles cannot move here and there. That's why the solids are very stable. That means they are strong. Yeah. As a result, they have very strong intermolecular attractions in between them. Right. So due to that reason, the solid particles will not move here and there. So they will be stationary. Is it clear? Right. In liquids also, the particles are tightly packed, but they are not in a they are in a random arrangement, not like in an orderly arrangement like solids. In solids, the particles are in an orderly arrangement. I think you have learned this in all of right. In liquids, they are randomly arranged. Right. So therefore, they are easy to move. They are easy to flow. In gases, the thing is the particles they are arranged randomly here and there. That means there are a lot of free spaces in between particles. Is it clear? Therefore, those gas particles they are free to move. They will be moving in random motions here and there at any place in the container. Okay. So those are the main properties of solids, liquids, and gases. In this unit, that is unit number 4, the gaseous state of matter. As it is mentioned in the topic, we are going to talk about the properties of the gases. That means we are not going to talk about the solids and liquids. We will be talking about the gases mainly. Right. So in this lesson, we will be talking two main equations. Right. One is the ideal gas equation. Other one is the equation of kinetic molecular theory. Right. So based on those two equations, we can predict almost all the properties of gases. Right. Now, those are the two main equations, but based on those two equations, there will be some more equations and laws that we need to learn. For example, we have Boyle's law, Charles' law, Avogadro law, ideal gas equation, right? Then the combined gas law. Likewise, there are laws that we have to know. Okay. So in each and every of those laws, what we do here is now we are going to find out the connection between the physical parameters of gases. For example, the physical parameters are pressure, temperature, volume, and the numbers of moles or the amount of gas. Right. So always there will be a relationship between those properties is being discussed from those laws. Right. So let's come to those laws later. Before that, let's learn about these states of matter. Right. Right. So you can write the topic gaseous states of matter. So before studying about the gaseous of matter, let's learn what matter is. Okay, you can write a subtopic matter. Subtopic is matter. Right. So let's define what matter is. Uh, as I have explained you earlier, matter is anything that occupies space and that has a mass. Right. That is called a matter. So let's try the definition of matter. You can write down. Anything that occupies space anything that occupies space and anything that occupies space and has a mass. Anything that occupies space and has a mass can be identified as matter. Can be identified as matter. To the same point, you can write down. Matter is composed of substances. Matter is composed of substances that can be seen and touched. That can be seen and touched. As well as the things that cannot be seen, as well as the things that cannot be seen and touched. Right. So in a new point, you can write down. Based on the composition and properties of matter, based on the composition and properties of matter, it can be subdivided into three main categories. That are solids, liquids, and gases. That are solids, liquids, and gases. Right. Right. So, which is there. Yeah, I told that. Right. So the matter can be divided into three categories. We have studied. We have studied.
Suddenly, she came with me under the global. She entered the global and she said she will come. But global is global. What did you go with?
So the matter can be divided into three categories. That is solid, liquid, and gas. Right. So we can divide it into three categories. That is solid, liquid, and gas. Right. So if we talk about the properties of them, right, solids, they have a fixed shape and a fixed volume. We know the solid function. For example, this marker pen, it is a solid. So it has a fixed shape. No? If we are going to change the shape, what we do? If we are going to change the shape, it will break. Why is that? Because there are very strong intermolecular forces between the atoms of this solid substance. Okay, so we can say therefore they have a fixed shape and the volume is also fixed. So they have a fixed shape and a fixed volume. And the liquids we know, in the liquids we do not have a fixed shape, but they have a fixed volume. For example, okay, now this water in this bottle, now say it doesn't have a fixed shape, no, that's why it's shape one side shape, the shape will be changed. But the volume, it's the same. If I put the same amount of water into a different container, it occupies the same volume, but a different shape. Is it clear? So therefore, liquids, they have no fixed shape. But they have a fixed volume. Right. In gases, what will happen? Gases, they do not have a fixed shape as well as a fixed volume. Right. Always they occupy the shape and volume of the container. Right. So we can say that no fixed shape as well as no fixed volume. It's clear. Right. So they occupy the shape and volume of the container. The liquids will occupy the shape of the container and they have a fixed volume. Is it clear? So now we are talking the properties of these three states of matter, solid, liquid, and gas. Right. So when we are talking about the intermolecular forces, right, as I have explained earlier, in solids, they have strong intermolecular forces of attraction. The solids have strong intermolecular forces. Then what about liquids? They have moderate intermolecular forces. No? Right. So they have moderate intermolecular forces. And the gases will have weak intermolecular forces. Is it clear? Right. So due to these strong intermolecular forces, the particles cannot move here and there. So once we supply some amount of energy, what will happen? Right. If we supply energy, now if I trap this one like this, what will happen? It gives a sound. Why is that? Because the energy that I have given to this one, it will vibrate the particles. That the particles will be vibrated. So due to these strong intermolecular forces, the particles can undergo vibrations, but they cannot move around. But into liquid, what will happen? If there's water, and if we hit water, what will happen? The particles will move here and there, and it will give the space for our hand to move. And that means those particles can float. What about air? Again, it can float. That's why we can move through the air. Now, around us, we have air. What if the air is also like a solid substance? Then you have to dig through the atoms and move. No? Yes, it's not easy to move. But if it is not air, if air is like solid. So those are the properties. So we are writing as a here in solid, we can say due to strong intermolecular forces, particles can vibrate. But cannot move around. The particles can vibrate, but they cannot move around. In liquids, what will happen? The particles, they can move. No? So particles can move. So, but it is not freely movable like in gases. But particles are free to move up to some extent. So we can say particles are free to move up to some extent. Right. In gases, what will happen? The particles are free to move. They can move here and there up to any limit. There are no limits. So those are the properties. Now, based on those properties, we can give the diagrams, the molecular diagrams of those particles for solids, liquids, and gases. For solids, so if we consider a sample, if we consider a solid sample, like this, so it has particles which are arranged close to each other in a random arrangement. Like this, the particles are arranged randomly. So there will be intermolecular forces between them. So they will help tightly with each other. Like this. So that is in solids. In liquids, what will happen? We have a sample. There are liquid particles which are randomly arranged. The particles are closer to each other, but they are not in an orderly arrangement. They are in a random arrangement. So as a result, they can move here and there freely. Like this, they can move here and there freely. If we consider gas, The particles are dispersed here and there. Right. That means they are more far apart from each other, and they are also freely movable. Like this. Is it clear? The particles are freely movable in this manner. Right. So you can copy this down. So this is the summary of the three states of matter. So it will be easy for you to study. Not done quickly. Right, have you finished copying now? Shall we continue then? Right. So then let's see. So when we are talking about these states of matter, now there are three states of matter: solid, liquid, and gas. So there will be interconversions between these liquid states. Right. That's for brightest class. Because poetry is Friday. It's bad.
No,
Why not?
the bioclass is there, OAS, physics class is also there.
Poetry.
Yes.
But Shadilati is upright. Yes. She asked me not to go because once those people from the Buddha Sasana Madhya came back, they have threatened.
Biology class and physics class is like that. The biology physics class, something like this.
Yeah, then there is all the other institutes, they all the class on Fridays. But this is the only sir.
Yeah, it's just like we went for exam.
Even I was like that, because I don't want to cancel the class, but since the institute is closed, what I am supposed to do?
Don't keep on going so that
Right. And you are not coming to class on Friday? So that message is for Friday class. All right. So there will be interconversions between these solids, liquids, and gases due to temperature changes. Right. Now we are going to discuss about that. Alright, I forgot something to tell you. Now, due to those strong intermolecular forces in between solids, right? Those solid particles are held tightly close to with each other. Right. As a result, what will happen? If we apply a pressure, will there be any compressibility taken place? No, it has zero compressibility. Solids cannot be compressed. Right. Then liquids. So those particles are also closer to each other. They too are slightly compressed. So we consider them as incompressible substances. But gases, now see, there are very high, that means there are very large spaces in between gas particles. Therefore, those particles are highly compressible. Oh, you are not seeing. Didn't you come to the bus? But on the last day, you promised to come.
Ya, ya. Mang ilang sa din ako.
Is it 100? Yes. Tomorrow morning we have this.
Ang pwede rin mo siya. Pwede kayo magkakapit to.
Right, so let's come to this lesson. I was thinking that she is coming to the class because last week she promised me to come to the class. So now we were talking about the compressibility. So solids, they are incompressible. Solids are incompressible. Liquids, they are slightly compressible, that is again we consider it an incompressible substance. The gases, they are highly compressible. So that is one of the right way. Yes, it's like this. Okay, right. So you better liquids can be compressed, but up to only a small amount.
Slowly, just like solids also can be compressed due to thermal
That means,
contraction.
yeah, they can be compressed if we apply those desired factors. For example, if we apply a very high hydraulic pressure, then the solids can be compressed. Now, here we are not talking about those extreme conditions.
Because like oil compress more than expands, like
Yeah, during thermal expansion, they can expand to some extent, but not very much. There's only slight expansion and compression, but that is negligible. But if we consider the gases have a remarkable compression. For example, if we take a syringe, like we have syringes, no? Right, and remove the needle and close the open end with your thumb and compress it. Compress the piston. What can you feel? The pressure can be felt, but the piston is compressed. You better buy your syringe today and just test it. Just pull the piston and close the open end from the thumb and press it. It will be compressible to a large extent. If you fill the syringe with water and compress, it's not. Is it clear? That's why we call them incompressible substances. Right. So if we apply very high, that is about 180 pascals, right? Then it will be compressed. It's okay. Right? But here we are talking about the general conditions.
What is 80?
Atmospheric pressure. Now the pressure that we felt from the atmosphere is called 1 atmospheric pressure. That is 1 atm. 1 atm is equals to 1 into 10 to the power 5 newtons per square meter or 1 into 10 to the power 5 pascals. Is it clear? So 100 atm means 100 times the atmospheric pressure. Is it clear? Right. So like this. Don't worry, we need those ATMs and all the things in the calculations in the latter part of this lesson. Did you do? You have started that lesson?
Yeah, she is like your female version. What? Even she is going same teacher style.
Okay, that's better. Right. So we can say that the solids, they are incompressible, liquids are incompressible, and gases are can be compressed to a great extent. Right. So we better write extremely hard to compress. It's better rather than incompressible. Right. So below this, I don't have space. You can write under solids. You can write down extremely hard to compress. Under liquids also extremely hard to compress. And under gases you can write can be compressed to a great extent. Right. Then let's discuss about this interconnection. Right. So we have the three states that are solids, liquids, and gases. Right. Solids can be heated and converted into liquid. Right. That process is called, what's the process? Solids into liquids. Melting, yes. Yeah, melting is the process, no? For example, ice melts into water. Right. So that process is called melting. Is it hard to feel? Yes. Right. So it is water in liquids. The liquids, they are converted into gases even by increasing the temperature. Right. What is that process is called?
Also, what's the difference between boiling and evaporation?
Yeah, I'll explain it. Right. This process is called evaporation. Liquids are heated and they will be evaporated into gases. I'll explain later.
We can't write evaporation, we should write boiling.
Evaporation takes place by boiling.
He said that things rather than boiling.
Boiling is the process. By boiling, evaporation takes place. Thank you. Then the gases are condensed. Gases are converted into liquids in a process called liquefaction. They are condensed. So the process is called liquefaction. Right. The process is called liquefaction. Then the liquids are converted into solids in a process called solidification. This process is called solidification. Right. Again, there's a process. Conversion of solids directly into gases. That process is called sublimation. Right. Sublimation. And gases are converted into solids directly. That process is called, what is that process? Conversion of gases into solids is called deposition. Right. Vapor deposition into solids. Right. So these are the 6 main processes that you need to know. Is it clear? Right. Now there are 2 processes called evaporation and vaporization. Those are 2 different things. Right. Evaporation takes place once we boil the substance. Right. Once we boil, the liquid will evaporate into gases. Okay. Then for the vaporization, we do not need to boil. Right. That means the gas particles on the surface gas molecules, they will absorb energy from the outer surface, right, from the outer environment, and they will be vaporized. They will be vaporized and not evaporated. Is it clear? Why not?
What is vaporization?
Vaporization. Right. Vaporization is just now think once we spill water on the floor. Right. After some time, what can we observe? It's been dried out. That means that liquid has been that means it's been vaporized. Right. It has converted into vapor and it's gone off. Did we boil that? Did we put fire below the water to evaporate it? No. That process, that means those water molecules, they absorb heat energy from the surface, from the surrounding environment, and they will get vaporized. Is it clear? Then evaporation is we place some water in a pot and put on the stove. Then what we do? We boil it. That means we supply heat from the bottom and we are evaporating of the water molecules. Is it clear the difference? For example, water in a tank, they will undergo vaporization. If we consider this Kurunagala tank, water vaporizes. It does not evaporate because we are not boiling water. We are not going to put the immersion heat and boil it.
I don't need to keep you something.
Yeah, it will get heated due to sunlight, but that's not the boiling process. Right, boiling is something else. There's a thing called boiling point. The boiling point is the temperature where the saturated vapor pressure equals to the atmospheric pressure. That means the vapors that are created due to the evaporation will create a pressure that is equal to the atmospheric temperature, atmospheric pressure. Then only that bubbling and boiling can be observed. Is it clear? Now at the sea level, what's the boiling point of water? What's the boiling point of water? Come on, you know it. 100 degrees Celsius, no? So that 100 degrees Celsius is applicable at the sea level. Right, at the sea level. Then the altitude is 0. Right. So once we go up, go higher a mountain, what will happen? Boiling point decreases. Decreases because once we go higher the altitude, the atmospheric pressure decreases. Why not? How does the atmospheric pressure is created? Due to the air column that is above us. So let's assume we have a mountain and here is the sea level. And here is the atmospheric uppermost level. Now here we have gas particles and this is air atmosphere. Now the pressure in this point at the sea level, that is 1 atm. That pressure is created due to the air column above this. Right? Due to the weight of the air column from here to here, the pressure will be created over here, that is 1 atm. Is it clear? So once we go higher the altitude, now let's say now we are at the Mount Everest, at the peak of Everest. So what can we say about the air column here? The height of the air column, it's less. That means it creates lesser pressure on here. That means once we go higher the altitudes, the pressure will be lower. Is it clear? Pressure decreases. So once the pressure decreases, the saturated vapor pressure that we need to create to tally with the atmospheric pressure decreases. That means the water boils at lower temperatures at higher altitudes. For example, water boils at 100 degrees Celsius at sea level. Now, what is the altitude in Kurunagala? As I remember, it is 119 or 120 meters above the sea level. I can't remember exactly, but it's 119 or 120. On those roads, road signs they have mentioned it. Right. And once we go to the hill country, what will happen? Once we go to Nuwara area, their altitudes will be several kilometers. No? Right. Then that means their atmospheric pressure is lower, so the water boils at lower temperatures. That's why in Nuwara area you can sip a tea which is what we call fuming without burning your tongue. That means you will see that the steam is coming out of the teacup, but it's not that much hot. Like that means usually water boils below 100 degrees Celsius in Nuwara area. That's why you are not asked to take any meat items from Nuwara area because the boiling temperature is low and they will not kill the pathogens in meat items. Okay, so it's like that. Huh? So did you understand how this, what's the difference between evaporation and vaporization? So the vaporization is an automatic process. We do not need to heat it intentionally. For the evaporation, we have to heat. Right. That process is called boiling. No? Is it clear? Right. So this is the interconversion between the matter, solid, liquid, and gas. Yes, Anna, what's your question? Now, I saw it like what is the sublimation of calcium carbonate? Is that so? Amna? So, did you find the answer? Ah, so it is not a very important thing. Right. So, did you understand this? Right. So, let's move on to the note again. Let's move on to the topic. Right. You can note down the subtopic interconversion of states of matter. Interconversion of states of matter. Right. You can note down matter in one particular state. Matter in one particular state can be converted into another state can be converted into another state by heating or cooling. Then you can note down the increase of temperature the increase of temperature makes the particles to move faster. The increase of temperature makes the particles to move faster. And as a result, the intermolecular distance will be increased. Therefore, if solids will be converted into liquids, solids will be converted into liquids, and liquids will be converted into gases. Solids are converted into liquids and liquids are converted into gases. Is it clear? Right. So in this diagram, it illustrates how the interconnection between different matters will take place. So you can write it. All right, finish. Right. Right, finish writing. So did you understand the definitions of these things then? What is melting, evaporation, solidification, liquefaction, sublimation, and deposition? Those are the 6 processes. So I'm not going to give you the definitions of them. I'm not needed.
Sublimation is what happens in dry ice.
What happens in?
Dry ice.
Yeah, dry ice. Yeah. Dry ice means it's solid ice. Solid carbon dioxide. So once we add water, it will directly give away carbon dioxide gas. So that is it. Solid into gas. So it's the same process that happens in those camphor balls, copper ball. Don't you know?
The thing that they keep carrying.
Yes, the things that we use to keep the insects away. Right. So there, we have that ball. After a few days, it's gone. The thing is, it is evaporated. That means it has sublimed. Is it clear? So that's the sublimation process. Right. Then those are the interconversions, and these are of not much importance. Now we are going to move on to important part of this lesson. That is the gaseous state of matter. Right. You can write the subtopic: gaseous state of matter. Gaseous state of matter, that is sort of right. The gaseous state is characterized by 5 important properties. Right. So there are 5 important properties of gaseous state. So let's learn about those properties. One is the gases are highly compressible. We learned it. The gases are highly compressible. Then the gas particles, they exert pressure equally in all the directions. That means if we have a gas particle over here, it exerts pressure in all the directions equally. Is it clear? That's why they are not moving here and there. They are moving randomly, but it's in a balanced position. Right. Then third one is the gases have much lower densities than liquids and solids. We know that solids are having the highest densities, but there are some liquids which have higher density than solids. For example, mercury. It has a very high density. Right. So, but the gases, they have very low densities than that of liquids and solids. Is it clear? Then the fourth factor is uh, the gases, they do not have a fixed volume and a shape. They occupy the volume and shape of the container. Okay. That's also a factor that we learned earlier. Then the other one is the gases, they mix with each other without any support from the outside. That means without any mechanical aid, they will mix together each other. Is it clear? That means if we place the sample of nitrogen in this corner and sample of hydrogen in this corner, and once it is allowed to mix, they will come and they will mix with each other without any mechanical aid. Is it clear? But in solids and liquids, we need to give additional support. For example, to make an alloy, what we have to do? To make an alloy, alloys means 2 or 3 metals that are combined together. So what we have to do? We have to melt it. Right? We have to melt it and then mix it and solidify. Right? So we have to place some layers and hammer it until they are get mixed and homogenized. Some mechanical support has to be given. In liquids, think of making a tea. Once we dissolve sugar, what do we do? If we place the sugar crystals and keep it to dissolve automatically, it won't happen, no? It will happen to some extent, but not that much. We put a spoon and stir it. That means that's the mechanical support that we give. But for the gases, it's not like that. Is it clear? Right. So let's learn about now. Let's write. Now we have learned about the five properties. Then let's write. Right. You can note down the gaseous state. The gaseous state is characterized by the gaseous state is characterized by the following physical properties. Characterized by the following physical properties. Number one is gases are highly compressible. Gases are highly compressible. Second one, gas molecules exert equal pressure in all directions. Exert pressure, that is gas molecules exert equal pressure in all directions. The third one, gases have much lower densities gases have much lower densities than the solids and liquids. Then the fourth one, gases do not have gases do not have a fixed volume or fixed shape. Gases do not have a fixed volume or shape. To the same point you can write down. They take the volume and the shape of the container. Right. So they take the volume and the shape of the container. With the fifth one, gases mix evenly gases mix evenly in all proportions gases mix evenly in all proportions without any mechanical help. Without any mechanical help. All right. So those are the 5 properties of gases that characterize the properties of them. Right. In a new point, you can write down then. Since the intermolecular forces between the gas molecules are negligible, the behavior of gases is governed by some general gas laws. Some general gas laws. These gas laws usually link the properties like pressure, volume, temperature, and amount of gases. Right. So there will be a link between those properties. So now from the gas laws we can determine those properties with each other. and we can find some parameters. So that's the thing that we are going to do there. In these gas laws, you will need the properties like pressure, volume, temperature, and the amount of gas. Now we need to learn the gas laws. Limiting reagent is the reagent which will be over first. That's it. Only you don't need to go for that. Yeah, it's nothing those things with the question.
Last week.
I gave you two tutorials regarding the chemical calculations. In there, we have discussed such questions.
We have discussed, I don't believe everybody is having ethics.
But I explained it over there. Now I can't remember the question, but those better.
That's the question, value. 21. It's
एक बार को मैं क्वेश्चन पेपर समझते हैं ये दोनों यूज से की क्वेश्चन सब करना है come on limiting reagent over whenever we note का दिन note
yeah, ages, like this.
so what is the limiting reagent? The reagent that will be finished first. That's it. If we react now, let's say if we react HCl and sodium hydroxide, they will react in the mole ratio of 1:1. If this is having 0.05 moles and this is having 0.1 moles, this will be over first. So that will be the limiting reagent. That's it. At least in the syllabus, they haven't specified to teach that because that's a small thing that you need to say.
I was there in class. I was smoothly announcing that. Yes.
So if you understand this one. Now,
Wasn't we were in class. When class periods in school.
now let's assume you are given 0.05 moles and 0.01 moles of sodium hydroxide. So they will react in the stoichiometric ratio of 1:1. So 0.05 moles of HCl will react with 0.05 moles of sodium hydroxide. Then nothing will be remaining over here. 0.05 moles will be remaining over here. Is it clear? Then HCl is the limiting reagent because it will limit the reaction. That's it. Usually, I will be giving a note regarding this in the unit 12. Because in the unit 12, we are discussing the equilibrium and all the things. That's the place we need this one. That's why.
In that case, due to the limitation, limiting the reaction,
It will limit the reaction and the reaction will stop at that point. Though we have excess sodium hydroxide, since HCl is over, the reaction will stop by that point.
So in the resultant solution, we will have water, NaCl and NaOH.
NaOH, yes, there will be excess NaOH. Usually, we are discussing this in unit 12. Of Lagrangian notes, but unit 12 लेके आप लोग करना है. करना नहीं बनाएंगे मेमोरी पावर कॉम्प्यूटर. Right. So now we are going to learn the gaseous state of matter. Now we learned the 5 properties, and now let's move on to the gas laws. Right. So write the subtopic under this one, that is gas laws. Right. You can note down under the gas laws. Under the gas laws, we will be discussing under the gas laws. We will be discussing the relationships between we will be discussing the relationships between the pressure, temperature, volume, and the amount of gas. Right. So we are talking about the relationship between the pressure, temperature, volume, and amount of gases under these gas laws. Right. So under the gas laws, we are going to first of all we are going to learn about the ideal gas and the ideal gas equation. Right. I told you that there are two main equations in this set, right? The ideal gas equation and the equation of kinetic molecular theory. So this is the first equation, that is ideal gas equation. So you better write the first one. Number one. Ideal gas and ideal gas equation. So the ideal gas equation, some people refer to as the equation of state as equation of state is also there, but in current syllabus, A-level syllabus, we are not using that term. We are using the ideal gas equation.
Sir, what is the mass of a neutron?
Mass of a neutron. 1.6 into 10 to the power minus 27. What?
There is a question in case of that in a true or false statement. But the mass of an electron is closer to
That is 1.67 into 10 to the power minus 27 kilograms.
It's not
Yes, I got it. In the first lesson, I gave the mass of a proton and said that mass of a neutron equals to mass of a proton. And their relative masses are 1 and 1. Might be an old question.
Yeah, 93 or
1993 means it's more than 30 years now. So they are not asking questions like that.
there was only like 1.6 in the
All right. So they are not going to ask simple questions like that now. That's the main thing, because now the competition is very high. In that means about 30 years ago, about 20,000 students wrote A-level in science stream. Now it's about 8,000. 80,000. So the competition is high. The opportunities are limited because this country hasn't been expanded and the population has been increased. So the competition is high. Right. Now we are going to learn about the ideal gas equation So sometimes the ideal gas equation is referred to as equations of state as well. So you better write it within brackets. Equation of state. Right. So first of all, let's learn what is an ideal gas. Before learning about ideal gas equation, right. What do you mean by ideal? What ideal mean?
It is even
The perfect. Perfect, that means without any drawbacks, without any errors, that is a perfect thing. That is what we call ideal. That means there are no any errors. So ideal gases means here we consider about the gases which have zero intermolecular forces between the gas molecules and which do not occupy a volume in the container or which do not have a mass. Yes. Ideal gas is a gas where there are zero intermolecular attractions between gas molecules. That means there are no intermolecular attractions or repulsions between gas molecules. Okay. And the gas particles will not occupy a volume and a mass.
in the case it won't be better.
Yeah, it won't exist. That's the thing. In that case, there are no such gases, right? Because we know that in each and every gas particles have intermolecular attractions between each other, and they will have a small mass and a volume. So that's why we call them real gases. The gases that have the real existence are called real gases. Ideal gas is a concept. It's a concept that means there is no real existence for the ideal gases. Is it clear? But no, there are no ideal gases. The gases can be converted closer to the ideal behavior, but there are no ideal gases. That means we cannot remove all the intermolecular forces between gas molecules, and we cannot. That means we cannot remove all the masses and volumes of the gas particles. They will have at least a very small mass and volume. Is it clear? So we call them real gases. Is it clear? But for our convenience, we consider the real gases as ideal gas. Right. At some particular values, that means at some particular condition, we consider the real gases behave ideally. And by assuming the ideal behavior, we can apply the ideal gas equation for the real gases. Is it clear? No? Is it clear? Right. So we just assume the ideal behavior. Is it clear? Right. So let's learn about ideal gases first. Let's try the definition of ideal gases. You can say when there are no intermolecular forces, when there are no intermolecular forces, among the gas molecules, when there are no intermolecular forces among the gas molecules, and the gas molecules do not occupy and the gas molecules do not occupy a volume or mass. No need to mention the mass, actually volume is enough. Do not occupy a volume of the container. That's why these are concepts. To find the relationships between the pressure volume, amount of gas moles and temperature. But when real gas can behave ideally, that's not the issue. Sorry, right? There are some other gas molecules, and the gas molecules do not occupy the volume of the container. Such gases are said to be ideal gases. Such gases are said to be ideal gases. Then we can say the relationship between in a new pointer, the relationship between pressure, volume, temperature, and the amount of gas moles pressure, volume, temperature, and amount of gas moles is given by the ideal gas equation. Is given by the ideal gas equation. Therefore, any gas which obeys the ideal gas equation or any gas which obeys the ideal gas equation is said to be an ideal gas. Right, so these are the parameters. Right, so these are the parameters. Now see, the ideal gas equation equals to PV equals nR3. So P is the pressure in pascals, P is the volume in cubic meters, N is the numbers of moles, the unit is mole, and R is the universal gas constant. It's a constant. The value is 8.314 joules per mass per Kelvin. It's a constant. And T is the absolute temperature, that is in Kelvin scale, not in Celsius or Fahrenheit. Is it clear? Right, so you can write it. All right, finish copying now. Right. So this is the ideal gas equation. So below that you can write down. The ideal gas equation is the a relationship among four variables. The ideal gas equation is a relationship among four variables. And it describes the state of any gas. And it describes the state of any gas. Therefore, it is said to be therefore it is said to be the equation of state. Is said to be the equation of state. Right. So let's see some calculations regarding this. Right. So you can write down this question. I'm going to erase this one. Question if hydrogen gas behaves ideally at 27 degrees Celsius and 1 atm pressure. If hydrogen gas behaves ideally at 27 degrees Celsius and 1 atm pressure in a 40 cubic decimeter rigid container. In a 40 cubic decimeter rigid container. Number one. Calculate the amount of gas molecules. That means the gas is H2, no? Let's say calculate the amount of H2O. Second one, calculate the mass of hydrogen gas. I'll give you a couple of minutes to do that. Right now, the first one, amount of H2 bonds.
To find mass should be substitute more or less mass or less.
Number of moles equals frequency values more than the equation that we do.
Yeah, I need to substitute that.
So did you find the first one? What's the answer? What's the numbers of moles? Okay, shall we see the first one? Calculate the amounts of H2 bonds. Right. Now, before writing the answer, we have to assume the ideal behavior because H2 is said to be behaving ideal. So therefore, we can apply P equals NR. If this statement is not given in the question, then we have to write the assumption. We have to write that assuming the ideal behavior of that particular gas species. Right. Since it is given, we don't need to write the assumption, otherwise we have to write the assumption. So we can apply PV equals nRT because this is an ideal gas. What we need to find out here is the amount of hydrogen moles, that is N. Then let's subject N. So N equals PV over RT. So pressure is 1 atm, that means 1 into 10 to the power of 5 pascals. because we have to apply the pressure in pascals. 1 atm equals to 1 into 10 to the power 5 pascals. Actually, 1 atm equals to this much of pascals. For our convenience now, this is once this is written in scientific notation 1.0135 into 10 to the power 5. So we take it approximately as 1 into 10 to the power 5. Now for calculations in gas loss, we can use the 1 atm as 1 into 10 to the power 5 pascals. Then volume is 40 cubic decimeters. That means 40.0 into 10 to the power minus 3 cubic meters. We have to apply it in cubic meters. Divided by RT, R is 8.314 joules per ounce per Kelvin. Into temperature is 27 degrees Celsius. That means 300 Kelvin. Because to convert Celsius into Kelvin, we have to add 273. Right. Then we can simplify. 10 to the power 5 means 5 zeros. Here 10 to the power minus 3. 10 to minus 3. 3's will be cancelled off. Then 2 will be remaining. Then those 2 zeros can be cancelled off with these 2 zeros. Then we will have 40 divided by 25. Okay, how did I get this 25? Because 8.314 into 3, that is 24.94. Once we multiply 8.314 by 3, the answer will be 24.942. For our convenience, we can take it as approximately 25. So that is a shortcut that we use in gases. Once it is always given, once it is as 8.314 into 3, you can get as 22. No one is going to go wrong in that. So then 40 divided by 25 will be 1.6. So this will be the numbers also. So these are numbers of moles of hydrogen. The second one, calculate the mass of hydrogen gas. Now we know that there's an equation, number of moles equals to mass divided by molar mass. Then to find out the mass, we can rearrange this one, number of moles into molar mass. Mass equals to numbers of moles into molar mass. So we can find out the mass of hydrogen. The numbers of moles we found it as 1.6. And molar mass of hydrogen is the relative atomic mass of hydrogen is 1. In hydrogen, there we have 2 moles, two hydrogen atoms. Therefore, it is 2. So we have to multiply by 2 grams per mole. Answer will be 3.2 grams. Is it clear? Answer will be 3.2. That's the mass of hydrogen. Okay, you understand?
The different questions like that we use this relative relative masses. They are supposed to be
I understand.
for questions like these
Okay.
where we are supposed to use relative molar masses.
Yeah.
They are giving
Yeah. Usually they will give the relative atomic mass. Then we have to find the relative molar mass from that. Okay. I think you know how to find out relative atomic mass. Sorry, relative molar mass.
I think so.
It's like this now. Let's assume you are given a compound like ethanol. That means this is 3 to 5 volts. Here we have two carbon atoms. The relative atomic mass of carbon is 12. Oxygen is 16. And hydrogen is 1. Sorry. You know how to find it. Then what did you say?
It's slight miscalculation of my part. Miscalculation.
Yeah. So the relative molecular mass can be found by finding this one. No? Since we have two carbons, it's 12 into 2. Plus we have 6 hydrogen, that means 1 into 6, and 1 oxygen, 1 into 60. Once you simplify, you will get the answer as 46. So that is the smaller answer. That's the thing that we have learned earlier. Okay, then so shall we try another question now? Shall we take a small break and start? It's better to get a small break, no? About 10.
Learning the break, save and replay.
Yeah. Let's take about 10 minutes break. Right. So then after that, let's start. Perfect. Now, after break, now we are going to start discussing another question. Right. You can note down the question. Question number 2. 3.2 grams of oxygen is placed. 3.2 grams of oxygen is placed in a rigid container at 127 degrees Celsius. In a rigid container at 127 degrees Celsius and 2 into 10 to the power 5 pascals pressure. Assume that oxygen behaves ideally. Find the volume of the container. Find the volume of the container. Second one, find the mass of oxygen required. Find the mass of oxygen required to be added or removed. Be added or removed from the container and then to change the temperature into 27 degrees Celsius and pressure into 1 into 10 to the power 5 pascals. This is the question. 3.2 grams of oxygen is placed in a rigid container. What do you mean by a rigid container?
So fixed.
Yeah, it has a fixed volume. That means that there is no any volume expansion or contraction. Correct. So 3.2 grams of oxygen is placed in a rigid container at 127 degrees Celsius and 2 into 10 to the power 5 pascals pressure. Assuming the ideal behavior, find the volume of the container and then find the mass of oxygen required to be added or removed from the container to change the temperature into 27 degrees Celsius and 1 into 10 to the power 5 pascal. Can you find the answer? Find it. I will give you 5 minutes. Do the calculation.
Don't you have an extra pencil?
Pencils, I don't have.
That's
Some
not even what I
I only have pens.
I gave them definitely some. Why your mom is teaching here?
Yeah.
Yeah.
We should want something like Sumeda Mani.
Yeah.
So
So we are done. It's very well. See,
it's another. Something. That's not yeah.
she thinks
Sure.
Wednesdays and Thursdays.
Did you learn from her? Yeah. Straight from Tamara. I think classes from grade 6 to 11.
If they have a business, if we
Yeah, 6 years. And she was our class teacher. Um, and she was our English teacher. And again, she came to teach us English, came to English
English teacher, English medium teacher, ask him to also anymore. So, she asked us to do the assembly. She gave us the responsibility. And like on Monday, I couldn't go and fever. And when she was saying, it is a mobile for the stand-up comedy thing, this after we left, right, and got cancelled. Or singular, they had gone there and be laughing on stage. This teacher, she got frustrated, she resigned at the stage. Now she teaches English for the whole LD section in families.
Asian, no?
Yeah, yeah.
I think that I'm mixing up. Shall we see the question? Shall we see the answers? Did you write the answers? Brandon?
Yes, sir. I am somewhat sure about the first one, but the second one is
So let's see how to find the answer. Find the volume of the container. Right. So we have given the mass. So it is placed in rigid container at 127 and 2 into 10 power 5 Pascal pressure. So you're going to find out the volume. Right. To apply the ideal gas equation, that is PV equals nRT, we need the numbers of gas molecules. But the mass is given, so therefore, first of all, we have to find out the numbers of moles of O2. That is mass divided by molar mass. Oxygen is 16, so O2 is 32.
I think it just has 60.
It has to be 32. Why? Because O2, there are 2 oxygen atoms. Yeah. So then this will be 0.1, right? So number of moles of gas will be 0.1. Then we can apply PV equals nRT and V equals nRT over T. So N is the number of gas molecules, that is 0.1. Numbers of moles. R is 8.314 joules per moles per Kelvin. And the temperature is 127 degrees Celsius means 400 Kelvin. Divided by the pressure, that is 2 into 10 to the power 5 pascals. You can simplify and get the value. Is it 1.6628? Yeah. Yeah. So what's the answer that you got? Let's see. Point 1. Here we have 10 to the power 5. That means we can cancel off 2 zeros over here. And this will become 10 to the power 3. Then we have 2. 2 times 2. Right. So 10 to the power 3, once it goes upwards, it will become 10 to the power minus 3. Okay. 0.1, 8.314 into 2 means 16.628. Okay, 16.628 into 10 to the power minus 1 is here, and once 3 comes up, it will become minus 4. Right, so minus 3 and minus 1 becomes minus 4. Huh? So it is 16.625 into 10 to the power minus 4. Usually, when writing scientific notation, we place only one decimal, one whole number. So it will be 1.6628 into 10 to the power minus 3, right? Cubic meters. So that will be the volume of the gas, volume of the container. Why? Simplifications are like.
When I'm reading cancel of the two.
Simplifications are like. All right. So answer will be 1.6628. Sorry.
This part B is also.
Yeah. 1.6628 into 10 to the power minus 3 cubic meters is the volume. The other one is find the mass of oxygen required to be added or removed from the container to change the temperature into 27 degrees Celsius and pressure into 1 into 10 to the power 5 pascals. Right. So now what has happened? Now we need to change the temperature into 27 and pressure into 1 into 10 to the power 5 pascals. So let's find out the numbers of moles of gas that will be required to maintain these conditions. Okay. So let's apply PV equals nRT. And from there we can subject in. So N equals PV over RT. So the new pressure will be 1 into 10 to the power 5 pascals. And volume is we found it 1.6628 into 10 to the power minus 3 cubic meters divided by R is 8.314 joules per moles per Kelvin. And the temperature is 27 means 300, no? 300 Kelvin. So once you simplify, you will find the numbers of moles. You can cancel out this. 1.6628 into 10 to the power minus 3, 16.628 into 10 to the power minus 4. Then 8.314 times 2 is 8.314 times 2 is 16.628. Isn't that so? Now we found it over here as well. Because 2 times 8.314 equals 16.628. That's it. So once you simplify, right, we have 10 to the power 5. So we can cancel off 3 tens from this 10 to the power minus 3. Then there are 2 zeros remaining that will be cancelled off with this. Right, we can cancel off them. And this will be 8.314 times 1. This will be 8.314 times 0.2. So the final answer will be 0.2 divided by 3. Answer will be 0.066. Point 2 divided by 3, answer will be 0.066 moles. So that will be the moles of oxygen required to maintain this temperature and pressure. But initially we had 0.1 moles. No? For the initial conditions, we maintain 0.1 moles. Did you understand? Now we need only this one. So that means this value is a lesser value than 0.1. That means we have to remove some of the gas moles from the system. Is it clear? So we can find out the difference. Therefore, the difference of gas moles, that is 0.1 minus 0.066. Answer will be 0.034. That means we have to remove 0.034 moles of oxygen from the container. Then we can say therefore we have to remove 0.034 moles of oxygen from the container. But in the question I ask is Find the mass of oxygen required to be added or removed. Now we know that this much of moles of oxygen have to be removed. So we have to find the mass. So therefore,
Isn't it 0.066?
0.066, yes.
That's a 0.006.
No, 0.2 divided by 3. Zero point two divided by 3. 0. Take the decimal place, that means here. Then to 2, we don't have any trees. Okay. 0 times 3 is 0. Then
0, 0, sir. That's not 0. But 0 to 7, you have reduced. You will have in the list.
the law of division method is there. Right. Then to 0, no 3s. 0 times 3, 0. 0 remaining. Then to 2, again 0. 0 times 3, 0. 2 remaining. To 20, we have 6. 6 times 3, 18. 2 remaining. For 20, again 6. 0.066. Right. So we need to find out the mass. The mass of oxygen to be removed. So we know that number of moles equals to mass divided by molar mass. So therefore mass equals to number of moles into molar mass. So number of moles is 0.034. And molar mass of oxygen is 32. Okay. You will get the answer as 1.088 gram. Is it clear? Is it clear? Yes, officer. Okay, now online is asking me what is the answer? What if the answer is taken for second decimal place? 0.06. Right. If we take 0.06, then the difference between these will be 0.1 minus 0.06. So that will be 0.04. So 0.04 will be multiplied by 30. So what will be the answer then? Yes, 1.28. So then that is erroneous, no? 1.28. So at least take the values up to two significant figures. Right. Right on the ending, I think it's clear for you. All right. So the answer will be 1.088. So that's all regarding the ideal gas equation. But this ideal gas equation that can be expressed in different forms. Right. Now we are going to learn about that. Right. You can note down. Is there any problems?
Only the I am getting 0.066. So always 0.060. I mean that I got the even from going.
This is 10 to the power 5. Here 10 to the power minus 4. We can cancel off this and only 110 will be remaining. Yeah, it is 10 to the power 3. Those are very simple mistakes. You are doing primitive mistakes. That means you are doing mistakes with maths, not with chemistry. If it is with chemistry, I am happy because then I can make you. But if you are doing errors with the simplifications, that means my advice is to go to another maths class, O-level maths class. එහෙම බැරි නම් මේ ටිකක් මහන්සි වෙලා calculations ටික හදා ගන්න වෙනවා simplifications. Is it clear? Okay, now see in these calculations we saw that once the different parameters are given, we have to apply it to the ideal gas equation. See, now first of all we calculated the numbers of moles of oxygen here as mass divided by molar mass. Is it clear? Mass divided by molar mass. So that is n equals m over n. The equation that we have used here is n equals m over n. Then what if we replace this n with this one? We can replace this n with m over n. Right. If we have replaced that with this, then we can directly use that equation for our calculations. Right. Is it clear? So likewise, we can find out different forms of this ideal gas equation based on the parameters that are given. So let's learn about those things now. Okay, you can note down. There are some insights. There are some insights into the ideal gas equation. There are some insights into the ideal gas equation that it can be expressed in different forms. It can be expressed in different forms to estimate the mass and density of a given gas. To estimate the mass and density of a given gas. Right. So let's see how this is done. So we can apply PV equals nRT. The equation is PV equals nRT. PV equals nRT. So we know that numbers of moles is given there. We can rearrange this equation like this. P equals n over V times R. What is n over V?
Is concentration.
Concentration. Numbers of moles divided by volume, that is concentration. Concentration equals numbers of moles divided by volume. So therefore, pressure equals CR. This is one form of the ideal gas equation that you can use. Is it clear? Then let's see the other one. We have PV equals nRT, and we know that number of moles equals to mass divided by molar mass. Mass divided by molar mass. So PV equals m over n times R. Okay. Then we can rearrange this one. Take m to this side. Tm samanayi. Mass divided by volume times R. So what is mass divided by volume? Density. Density equals to mass divided by volume. So we can rearrange this one. We can say that Pm equals then DRT. No? Pm equals DRT. So if we need to give pressure, that will be DRT over M.
So I think when you are taking the volume to this side, if the applies forward, we can in R and now you're taking the volume that was in that side.
Yeah. Yeah.
They need the applies for R and D also. In the volume is
Here's some multiplication. Not addition or subtraction. It's a multiplication. Again maths. Right? So this Pm equals DRT. So we can rearrange this one as pressure equals to DRT over M. So we can express the pressure if we know the density and the molar mass. Capital M is the molar mass. So likewise, we can rearrange this equation. Okay, we can copy it down. Quickly copy it down. Right, have you stopped them? Okay, so then let's move on to the next part of this lesson, that is the Boyle law. Now that is all regarding ideal gas equation. Is it clear? Are there any doubts regarding ideal gas equation now? Right. You better study at home, and if you find any doubt, just ask me at the same point. Huh? Send me a message. So then the next law, that is the second one, that is Boyle. You can write the second law, that is Boyle law. Right. So this is also called the pressure volume relationship. Right. Because the relationship between the pressure and volume is given using this law. Why do we call it the Boyle law? Yes, the person who discovered this law was the Robert Boyle. His name was Robert Boyle. That's the reason. Right. So he said that Robert Boyle said that the pressure of a fixed mass of a given gas, pressure of a fixed mass of a given gas at a given temperature, at a constant temperature, is inversely proportional to the volume. Why? The pressure of a given mass of a gas at a given temperature is inversely proportional to the volume of that gas. So, once the numbers of moles and the temperature are constant, pressure is inversely proportional to the volume. P is inversely proportional to volume. So this is the relationship that was proposed by Boyle. You don't have this for the O levels, no? Boyle law and Charles law? No.
In calculation things and.
No, you don't have. I know. I know your syllabus, so you don't have. But when yeah, but
I saw those someone and got scales. You were feeling it.
we started a new thing. That's
All the classes.
Telnatic was doing it. There were some requests for me to do to start all our classes, so I had an alliance with Telnatic. We had to meet.
That's what they say in school for the.
Sorry.
That's what they say in school for the skills. Well, yeah, they used to get and they go feed to whatever or you already know.
Yeah, I know that. That's the same reason why that I started, because most of the students they come to A level without a proper background knowledge. So I want the oral students to get that proper knowledge and come to A levels. Yes. If there are some brothers and sisters, yes, then matters. It's a very quick revision class regarding these names. Right. Do you know some people like that? Yeah.
I don't make a mistake.
Right. So let's come to this one. So pressure is inversely proportional to volume. That was said by Robert Boyle. He said that pressure of a given gas is inversely proportional to volume, and then we can remove this proportionality by adding a constant. Right. So I asked that because when I was doing O level, we learned the Boyle law and the Charles law in O levels. Yes, we had Boyle law and Charles law, as well as the ideal gas equation as well. Right. So we can add the constant over there. So pressure equals constant divided by volume. Is it clear? So that is the boiling water. So we wrote the definition, na? Right, okay. Then we can note down. At a constant temperature, at a constant temperature, the pressure of a fixed mass, the pressure of a fixed mass within brackets amount pressure of a fixed mass amount of a gas is inversely proportional to the volume of a gas, the volume of the gas. You can write it. P is proportional to 1 over V, so P is equals to constant divided by volume. Then you can say the ideal gas equation can be used. The ideal gas equation can be used to derive the Boyle's law. The ideal gas equation can be used to derive Boyle's law. Now we apply Pg equals nRT. Now the constants are there. Numbers of moles is a constant and temperature is a constant. Those are the conditions. And universal gas constant is always a constant. No? So all these are a constant. That means nRT is a constant. So therefore, the PV product will be a constant. Is it clear? Isn't that so? Is it clear or not? Well,
This is clear, but the theory that an an inversely proportional equation can be made equal by using a constant. Then I'm not familiar with it.
right. So that means there's a proportional thing. A proportional can be removed. Proportional relationship can be removed by adding a proportionality constant. That's it. That means once we multiply this part by the constant, then it will be equal to this part. So that's the maths. That's okay. That's it. So once we apply the constant, pressure equals to constant divided by volume. Is it clear? But now we can apply P equals nRT. Then nRT all are constants. Therefore, the product of this is also a constant at that condition. Therefore, PV is a constant, or we can rearrange this one. PV equals to constant. By the cross multiplication, we can rearrange this one. Right. So PV is a constant. So if we consider two situations where in the initial situation the pressure is P1 and volume is V1, and in the second situation pressure is P2 and volume is V2, then we can equalize those two situations that P1 V1 equals P2 V2. Is it clear? Right. So if I write this, then I can explain that. Right. Then we can say if a fixed amount of a gas if a fixed amount of a gas at constant temperature, capital T, at a constant temperature, capital T, occupying a pressure of P1 and volume of P1, occupying a pressure of P1 and volume of V1, undergoes a change so that pressure becomes P2 and volume becomes V2. Pressure becomes P2 and volume becomes V2. Then according to the Boyle law, V1 equals to V2 is equal. So by comparing two situations with different pressures and volumes, we can say that P1 V1 equals to P2 V2. So then let's see. Now we can represent these relationships graphically. Right. We are going to do that. You can note down the Boyle law relationship. The Boyle law relationship can be expressed graphically as follows. Pressure versus volume. So we are going to express pressure versus volume. Now see, pressure is inversely proportional to volume. That means once we increase the pressure, volume decreases. Once we decrease the pressure, volume increases. So there will be an exponential relationship over here. Right? So we can draw it. At higher pressures, volume is less. At higher pressures, volume is less. At lower pressures, volume is high. So it will be changing like this. Yes. The change of pressure versus volume will be a curve like this. That means at high pressure, the pressure is high, volume is less. At low pressures, volume is high. So it is an exponential curve. Is it clear? So this is at a given temperature. Let's say this is at 200 Kelvin temperature. For a given gas at 200 Kelvin temperature, this will be the curve. Right. Then if we increase the temperature, here the temperature is constant throughout this 200. If we increase the temperature, the shape of the curve will not be changed, but it will be going somewhat. So let's say that is 400 Kelvin. So that is at 400 Kelvin. If we increase the temperature further, then the curve will be like this. So once we increase the temperature, the exponential will be this. Right. Then there's another one. There is a Boyle law that we know that P equals K over V. P equals K over V. So this is Y equals mx type equation. P equals K times 1 over V. Right. That is what we call P equals K over V. That means this is Y equals mx type. No? So if it is a Y equals mx type equation, that means if the graph is a straight line going through the origin. Give me a second. Right. So it is Y equals mx 5. So that should be a graph. That means the graph is a straight line going through the origin. So it's like this. If we plot pressure versus 1 over volume, pressure versus 1 over volume, it should be a graph like the straight line. So at lower temperatures, the gradient is low. Once we increase the temperature, the gradient will be increased. Like this. Basically, for the same gas, if we increase the temperature, the gradient will be increased like this. Did you understand it? Yes, some. And did you or
But it's I don't know. I can explain that in the
but we can do an example. Now, did you understand the graph?
When I understood what, in why does it change so drastically when it becomes one over?
Because P equals constant and 1 over V.
Yeah.
That means it is the Y equals mx type equation. So in mathematics, you have learned the graphs. The Y equals mx types are
Still,
the straight lines going through the origin.
but in this also,
That's what we do. There is pressure versus 1 over V. So that is Y equals mx type.
so maybe this one.
Pressure versus volume. So
For the.
that's mathematics thing. That's a change of graph.
This is coming exam.
Yeah, usually they will ask this for MCQs. The shapes of the curves. Usually that will be asked in the paper. Right. Now you can copy down these two graphs. That's how we represent this graphically. Right. Have I reached copying now? Okay. Right. Then shall we see a question? If you have reached copying down. Right. So you can note down the question. You can note down. The volume of 0.2 grams of nitrogen gas the volume of 0.2 grams of nitrogen gas at 273 Kelvin. At 273 Kelvin and 1.2 atm pressure. One point two atm pressure is 5 cubic meters. It's 5 cubic meters. If the pressure is increased to 10 atm, if the pressure is increased to 10 atm, while keeping the temperature at a constant level, while keeping the temperature at a constant value, calculate the volume of gas in cubic decimeters. Cubic decimeters. Within brackets, you can write down nitrogen gas behaves as an ideal gas. Within brackets, you can say nitrogen behaves as an ideal gas. Try to find the answer. First of all, see what are the constants and what are the variables. Then you will understand. What are the constants? Temperature and mass means amount of the gas. So it says the volume of 0.2 grams of into gas. Right. So there's no any mentioning about the change of this mass. At 273 Kelvin and 1 atm pressure is 500, sorry, is 5 cubic decimeters. This is also kept constant. If the pressure is increased to 10 atm while keeping the temperature at a constant value, say, keeping the temperature at a constant value. Right. So if the temperature and the amount of substance is constant, what can we say? Yeah, we can apply the pressure volume relationship. That is the boil.
And right the stage.
No, not even step.
Then we are
Yeah, then you can say using the boil law, apply the boil law. Right, no need to write these circumstances.
then only that part.
Yes, that part you have to say. Using boil law. Then we can apply the boil law. But so let's see. Let's do it.
What's the elements? Nitrogen,
For
40
40.
P.
Yes. Right, did you find the answer? I think the time is in. Right. So we can apply the Boyle law. So we can say applying Boyle law. By using Boyle law. We can say now two different equations are there and we can apply P1 equals P2 P2. Now the initial pressure is 1.2 atm, so it is 1.2 into 10 to the power 5 pascals, right? Because 1 atm is 1 into 10 to the power 5, so 1.2 is this into volume. The volume is 5 cubic meters. That is equals to T2. The second pressure is 10 atm, so that is 10 into 10 to the power 5 pascals. And we don't know the new volume. That's the thing that we need to find out. Let's say we do. So once we simplify this one, 10 to the power 5 and 10 to the power 5 gets cancelled off. 5 times 1, 5 times 2. Then V2 will be 1.2 divided by 2. That means 0.6 cubic meters. That's it. 0.6 cubic meters. Yeah. So the answer is asked in cubic decimeters. Then you have to convert this in cubic decimeters. 1 cubic meter equals to 1000 cubic decimeters. Therefore, that has to be 0.6 into 1000, that is 600. Huh? 600 cubic decimeters is the final answer. Did you get it? All right. Right. So that's the end of the Boyle law. I think that's enough for today. So next week we'll be discussing Charles law, Avogadro law, combined gas law, and then how to determine the molar volume and those things. Right. So then this will be the end of the class for today, and let's meet up next week.
Then tomorrow